Hi, I'm Mohit, and I'm going to present a work on relational learning for skill preconditions. Skill preconditions tell us when can we execute a given skill. For instance, given a cutting skill, we would like to know if the skill can be executed in the current context to achieve desired outcomes. As seen in the following videos, although there are multiple objects in both videos, none of the objects on the left impede the cutting skill. While for the video on the right, it is not possible to execute the skill without accidentally damaging the bell pepper. In this work, we want to learn such skill preconditions in a data-driven manner. There are two main challenges associated with this setting. First, we want to operate in diverse real-world settings, wherein objects can have arbitrary shapes and sizes. Additionally, each scene can have variable number of objects, and we want precondition models to be able to generalize to all such settings. Second, it is important to learn these preconditions from as few samples as possible. It is clearly impossible to expect to slice thousands of food items to learn preconditions of the cutting skill. In this work, we achieve this by using structured scene representations. Structured representations decompose a complex manipulation task into its constituent objects and their pairwise relations. Structured representations are important because of their low dimensionality. On the other hand, efficiently learning precondition models directly on high-dimensional perceptual input will have high sample complexity. In this work, we focus on learning relational representations between object pairs. Our main insight to learn these representations is based on interactive learning and the fact that objects which interact with each other in similar ways should have similar relations between them. For instance, in the following videos, although the blue object is always above the yellow object, their interaction leads to very different outcomes. In the left video, the object will sit stably on the yellow cube, while in the right video, the object experiences a large amount of torque. Hence, although object relations between these scenes seem similar, they are indeed quite different. Based on this insight, we generate a large set of pairwise object interactions in simulation. Using these interactions, we create a contrastive loss. Specifically, we use the triplet loss, which requires us to find both positive and negative scenes for a given anchor. We find these scenes based on interaction effects, which include position and orientation change and contacts. The following is our network architecture. We only use the initial part of this architecture for downstream precondition learning. We refer to this as FREL. Given a learned relational representation FREL, we use graph neural networks as a precondition learning model. The input to these GNN models are the output from the learned relational model. We note that we do not fine-tune our learned relational representations during precondition learning, which happens on real-world voxel data, and we use the same FREL across all precondition learning tasks. We evaluate our approach on three different tasks. First, we look at the task of sweeping objects in a line. Next, we look at the task of initial pre-cutting food items. Finally, we look at the block unstacking problem, wherein the agent has to predict if removing a certain block will still result in a stable configuration or not. We compare our approach against three different methods. First, we use a precondition model that works directly on high-dimensional 3D input. We also verify the performance of directly using discrete relations. Finally, we evaluate a real-to-sim approach, which operates by importing a real-world scene into the simulator and executing the skill in simulation to see if it achieves desired outcomes. Through our experiments, we find that visual baselines perform poorly on out-of-distribution samples. By out-of-distribution, we refer to the scenario where test set contains larger number of objects than the trained set. We observe that performance of pure visual baselines increases rapidly in such settings, while discrete relations perform poorly because of their inability to model complex scenes. For instance, both sets of scenes in the following figure have similar discrete relations but different precondition outputs. For the left set of the scenes, the orange block is always above the blue and black blocks, but only if we remove the black block from the right scene is the scene unstable. Additionally, we find that real-to-sim baseline is severely affected by perceptual errors associated with real-world voxel data. These errors, which include effects such as objects being embedded into each other or additional voxels along edges or corners, often result in incorrect predictions, as can be seen in the following videos. Although the simulation correctly predicts stability on the left video, it completely fails to predict it on the right two videos. In this work, we have looked at learning preconditions of complex manipulation tasks by decomposing them into their objects and pairwise relations. We use self-supervised interactive learning to learn a relational representation between object pairs. We show how this relational representation, learned completely in simulation, allows us to learn preconditions for three very different real-world manipulation tasks. Thank you.